This time I'm going to be really careful not to put my hand over the microphone. So here's hoping I remember during the video. This video is going to be about sea surface salinity. Actually, that's not true. It's going to be about salinity in general, both at the surface and at depth. So let's start with sea surface salinity. If you want to pause the video and go back and relook at the evaporation latitudes, because I'll be talking about them a little bit, and you may want to look them over first, go ahead. Let me talk about this graph first. So this picture, this figure 520 is in your book, and I'm going to be talking about it for a couple slides, so let's make sure you understand it. Clearly, there's the globe, right? And there's a graph next to it. Well, the graph corresponds exactly. So this axis of the graph is latitude. Notice here's the equator. Well, here's the equator. And here's basically the poles, and there's the poles. I drew crooked, but they line up precisely the way that they were made. Additionally, along this graph, there's also a bottom axis, which is salinity, going from lower salinity to higher. And, well, we'll talk about it only briefly. There's also a very little tiny axis over here for temperature. Temperature's in the red line, and sea surface salinity is in the green line. So, hopefully you get that. So, we're going to talk about how sea surface salinity varies depending on latitude. As a matter of fact, it's one of the strongest factors that controls it. So when we're at high latitudes, and high latitudes is basically the poles, we're going to be looking at this end and this end. 60 to 90, give or take, we would call high latitudes. You'll notice that there's this and this. This comes down here. This comes down here. Sea surface salinities are at their lowest values along this scale. When we're at the poles, either here or here. And why is that? Well, there's a couple things, and we'll talk briefly about why they're not as low. The first one, there's a large amount of precipitation in this area. They're right at the edges. Remember that the precipitation latitudes sort of were in this area. They're right at the edge of the precipitation latitude. So while they don't get a lot of the precipitation, they do get some of it. They get a large amount of the runoff. Now, in North America, in particular, the runoff from basically this entire area enters into this area and creates low sea surface salinity. Fresh water will sit on top of saltier water. So that's why it is so very, very fresh compared to elsewhere. It's slightly less fresh in the Arctic, and maybe you can guess why when we're talking in this area. No rivers in the Arctic, or very few, really. So there's no place for there to be the volume of runoff that we get in this big area where you can see all this water and all this land and all this coastline. So hopefully that makes sense to you. But even in Antarctica, it's still fresher than it is anywhere else. And that's almost universal regardless of the time of year. Additionally, in both these areas, it's a lot cooler. So even though there may be abundant sunshine, besides sunshine, we need heat in order to make water evaporate. So there's just not the evaporation necessary in order to, salty that water up. In the winter, you may get a slight period of time where it does get saltier. And this is due to the fact that when you have freezing of sea ice, sometimes the salt can get expelled. But even in the winter, it's not enough to bring the salinity up to what you would expect it to be in the more temperate latitudes. Now we're going to talk about this region. So basically, I'm sure you remember from looking at the maps, in here there was a little bubble of salty, and in here. They're not precisely centered around the Tropic of Cancer and Capricorn, but they're pretty close. And those are... Oh, I drew the lines badly. This goes here, this goes here. So we're talking about this point and this point. And those are the highest sea surface salinities that we've found. And they are due to the fact that there are very warm, dry airs in the area. This is an atmospheric circulation pattern. If you want to know more about it, we can talk about it in class. But basically, those cells, those Hadley cells I mentioned very briefly in class, causes warm, dry air to move across the area. And sometimes the winds can really, pick up. And for those of you in Miss Ung's environmental class, you probably talked a little bit about rain shadow, which can affect it as well. So we get very little precipitation. But because of its proximity to the equator, especially, along the Tropic of Cancer, Tropic of Capricorn, we have massive amounts of evaporation. So the water that's left behind is very, very salty, and you would expect it to be as salty as it is on the planet, and it is. There is an exception to this. This is very true in the Northern Atlantic, Southern Atlantic, somewhat true in the Southern Pacific, but while it is saltier, it is not to the same degree in the Northern Pacific. There are a bunch of different reasons for this, but we're going to talk about El Nino, La Nina, and monsoon, but those are the main reasons why the Northern Pacific does not quite follow the same curve of increased salinity there. And then we get down to the equator. So here's the equator. And the equator has lower salinity again. Still, we have a good amount of evaporation there. But we also have, especially in the southern Atlantic, a very large amount of runoff. And as a matter of fact, kind of on either side of the equator, there's a large system of rivers. Maybe you know the one. But the Amazon discharges right here. And the Amazon, even though, compared to the ocean's volume is tiny, is enough to keep, and even the Congo over here, are both enough to influence the area and provide so much runoff from the continents to keep salinity lower than it would be based on just evaporation rates alone. And even in the Pacific, we see this as well, especially along this side. It's actually quite fresh, and on the far side of the Pacific, we have the same phenomenon. So that's sea surface salinity. This is the picture you saw in the globe of global sea surface salinities from your book. It's pretty good. It doesn't, I think this is for August, but it's a general sort of picture that doesn't change a whole lot globally. But again, notice those highly salty areas in the middles, even in the Pacific. And then notice lower, very fresher water in here, down here, and then medium in the middle, right along the equator. And there are obviously the continents influence this, and it's not a perfect example, but it's pretty good. Now, salinity varies greatly at the surface, and we talked about this. We talked about all of the factors that, could affect it. But it varies very little in the deep ocean, and the question you should ask yourself is why? Well, go back to those things we talked about that affect salinity. What affects salinity? What are the processes? There's 3 that increase it and 3 that decrease it. And all of those are basically due to interactions with coasts or interactions with, like rain in the atmosphere. So they don't happen in the deep ocean because the deep ocean doesn't really interact with coastlines or with the atmosphere in any way. So what are the 6 that increase salinity? Evaporation, sea ice freezing, I'm forgetting one. And additionally, the ones that can lower salinity, precipitation, runoff, all of those things. So make sure you know them. We'll talk about them in class. So let's talk about salinity with depth. A lot of you complained about, the big scary, the profile. You're going to have to get used to them. This is the ocean surface, so it's 0. This is depth or pressure. It increases this way. And this is the variable. Now, what they did to measure salinity is what we do. They took a CTD. They had a little boat. So if this is really, them, they're out on the ocean. They have a little boat. There you go. And they drop a CTD off, and as they go down, it takes a value. Here, 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 and so on. And then they enter all those values, and they have different salinities. So at the surface of the water, the salinity may have varied quite a bit. And suppose you were here. We are in that area where you would expect fairly high sea surface salinities, and if you ever went out in the actual ocean as opposed to the bay, you would see that. So our sea surface would be around here. And once we got past the halocline, now you remember what the thermocline is. Thermocline is where temperature changes rapidly with depth. So halocline is where salinity changes rapidly with depth. And because they're both related to density, they tend to occur in the same spot, that same, somewhere between 200 and 1,000 meters. Ours would look more like this. Oh, I drew that badly. Let me redraw that. Ours would start out saltier and then follow the same curve once they do. Mid latitudes. That's us. So let's talk about it. So at high latitudes, we start fresher, get saltier, and then continue down. Along the Tropic of Cancer, right here, And then very low latitudes would probably be more like this, like the equator. And get rid of all of them. Once you get much below that halocline, once you get below basically 1,000 feet, the salinity is basically uniform. There's one exception to this that we'll talk about when we do masses of water, and that's in the Atlantic due to the salinity of the Mediterranean Ocean. But we'll talk about that exception when we get to it. We've talked about this a little bit, seawater density, but the density is a function of both temperature, salinity, and pressure. We've talked about the relationships before. They're given here again because in the next video we're going to talk about temperature and density and circulation of the ocean related to all the things on this page. So I'm going to stop here.